Bismillah. Welcome back to ThinkMath. Today's exam-style problem covers rational functions, quadratics, and finding intersections. All classic IB Math AA topics. 6 parts, fully worked. Let's go. We have f of x equals x squared minus 6x plus 9 over x minus 3 for x not equal to 3. Part A, sketch y equals f of x, labeling intercept and any asymptotes. Part B, write down the range of f. Then we introduce g of x equals x squared plus bx plus c with an axis of symmetry of x equals 1 and roots at negative 3 and q. Part C, show that q equals 3. Part D, find b and c. Part E, find the y-coordinate of the vertex of G. Part F, find the number of solutions of f of x equals g of x. Part A, before we sketch, let's simplify f. Look at the numerator, x squared minus 6x plus 9. We need two numbers that multiply to 9 and add to negative 6. That's negative 3 and negative 3. So it factors as x minus 3 all squared. That gives us f of x equals x minus 3 all squared over x minus 3. For x not equal to 3, we can cancel one factor of x minus 3. This simplifies to f of x equals x minus 3. But here's a crucial detail. X equals 3 is excluded from the domain. So, graph is a straight line, y equals x minus 3, but with a hole, an open circle at the point x equals 3. What does the graph look like? The y-intercept. Set x equals 0, y equals negative 3, so we plot 0, negative 3. The whole. At x equals 3, the function is undefined. Y would be 0 there, but we mark an open circle at 3, 0, not a filled dot. The slope of the line is positive 1, so it's a straight diagonal line rising steadily from left to right, interrupted only by that single hole at x equals 3. Part B, the range. What y values can f actually produce? Since f equals x minus 3 for all valid x, it can output any real number except the value it would give at x equals 3. At x equals 3, the output would be 0. But since x equals 3 is excluded, 0 is never in the output. Therefore, the range of f is all real numbers except 0. Part C. The roots of G are negative 1 and q. The axis of symmetry of a quadratic always lies exactly halfway between its roots. So the axis of symmetry equals negative 1 plus q, all divided by 2. We are told this equals 1. Multiply both sides by 2, negative 1 plus q equals 2. Add 1 to both sides, q equals 3. Shown. Part D. We know both roots are negative 1 and 3. For a monic quadratic leading coefficient equals 1, we can write g of x equals x plus 1 times x minus 3. Expand. X times x is x squared. X times negative 3 is negative 3x. 1 times x is x. 1 times negative 3 is negative 3. Collect like terms. X squared, then negative 3x plus x is negative 2x, then negative 3. So g of x equals x squared minus 2x minus 3. Comparing with x squared plus bx plus c, b equals negative 2 and c equals negative 3. Part E. The vertex lies on the axis of symmetry at x equals 1. Substitute into g. G of 1 equals 1 squared minus 2 times 1 minus 3. That's 1 minus 2 minus 3, which equals negative 4. The vertex is at 1, negative 4. The y-coordinate is negative 4. Part F. How many solutions does f of x equals g of x have? We substitute the simplified form of f, that's x minus 3 on the left. And g of x is x squared minus 2x minus 3 on the right. But remember, x cannot equal 3. Setting them equal, x minus 3 equals x squared minus 2x minus 3. Bring everything to one side, 0 equals x squared minus 2x minus 3 minus x plus 3. Simplify. 0 equals x squared minus 3x. Factor. 0 equals x times x minus 3. So x equals 0 or x equals 3. Now check. X equals 3 is excluded from the domain of f. That's where the hole is. So x equals 3 is not a valid solution. That leaves exactly one solution, x equals 0. 6 parts, every step explained. This is how you approach multi-part exams questions systematically to earn full marks. If you'd like personalized IB coaching with me, the booking link is in the description. See you next time.